nanohub.org.
Online simulation and more for nanotechnology.
With the image analysis tool, we have actually started doing machine learning studies using UNet model. So what it does is, what we do is we take images where we have graphene, and then we use k-means or template matching, the methods that we spoke about in the image tool, to find regions of graphene. Once that is done, we use this image as training data to upload it to our neural network. And once we train this neural network, we form a model such that we will be able to we are able to actually find out regions from an image directly and say that, okay, this region has graphene versus this region does not. And we have currently done this. And this is, we use a UNet model to achieve this. And we have trained as 58 images as far, and we have also used some augmented images. So these were not actual images, but we made them. And then we have found that our overall accuracy of the model as of now is 92%, and a precision is 88%. By accuracy, we mean that how many predictions of the model are correct. And by precision, we mean that what is the proportion that was identified correct. So in other words, accuracy is whether it is able to find all the graphene that is present in the model, present in the image, and precision is how correctly is it able to actually determine all the areas that has graphene. So, for example, over here we have high pressure. Over here we have high precision and high accuracy as well. It is able to identify. So this. Okay, this is our SEM image. This is the mask that we made using k-means, and this is the mask that the UNet model was UNet model gave out. And over here we can see that the UNet model was correctly able to identify that there is graphene present over here, and it was also able to correctly give all the regions that has graphene. Like it was correctly able to identify the whole hexagon. When we move down, we see that it was able to identify most of the graphene regions, but it actually identified more areas. And that is why we say that it has low precision. And then we move here and we see that it has low accuracy because it's not able to identify most regions where graphene is present. So graphene is basically this darker contrast over here, and the lighter contrast is the substrate. And it is not able to identify all the domains that have graphene, but if it is able to identify the graphene domain, it has a high precision of making the whole structure being available. And over here, we can see that it just doesn't know where graphene is. Like, for example, this is the only region where we have graphene, and this is where the model currently fails. And we are currently, and this is still a work in progress. So we are still working on improving this model, and we would we will have to work on a lot more images than the current number to have actually a very good model being developed. And at the end, I just want to show you that how the neural network actually identifies that whether graphene is present or not. So neural network is basically a black box, so we don't know what happens inside, but you can obviously say which pixels are actually determining whether graphene is present or not. So what it does is it identifies the edges of the graphene, and then it moves forward and says, if you can see that this was the substrate attribution. So it finds first the gradients where there is a color change, so intensity change. And then it says that, okay, this is a darker region, and there is a different intensity over here versus here. And that's how it identifies graphene. The good part about, or the interesting part about this is that this is how human brain also works. So human brain first identifies the edges and then sees that, okay, this is a different shade. And that is why we think that graphene is also present over here. And with this, I would like to end by saying that Gr-ResQ is a very powerful platform, and when adopted by the community, it could lead to rapid advancement in graphene manufacturing and production using data-driven analysis. So yes, the tool is still in its nascent stage, and we would love to have your feedback. If you feel that we have missed very important parameters, or if you have ways to make the tool more user-friendly, or just enhancements and improvements in general, you can either mail us, you can actually use a review or a wish list or a question options, which is available on the main tool page, and you can put in your comments over there. And since this framework is very flexible and expandable, and we are continuously updating it, we believe that a similar approach can be adopted for production of all other 2D materials by CVD in a scalable, sustainable, and a cost-effective manner, enabling faster realization of technologies through 2D materials. And I would like to thank you, and if you have any questions, I would be happy to answer them. A more general question: what is the best graphene you obtained so far? What is the lateral size with data mining? What about the lateral size of the single crystals? As of now, we have not actually data mined on recipes still. So we are still trying to increase the number of recipes that we have, and then we are going to connect the results of the SEM images as well as Raman, and then find parameters that are important and then move forward with that. But as of now, we haven't done data mining on just recipes right now. Our main focus is on the image tool and Raman tool, and automating the Raman tool as well. What about the lateral size of the single crystals? I think that connects to the previous question.
But Mitisha, maybe you can answer the question, like what is the typical lateral size of single crystals we get right now on copper, for example?
On copper, we actually get about, I think there are a few experiments that result in 100 microns. So those are huge graphene crystals. But in most normal growths, it's about 20 to 30 microns. Huge, yes. You can obviously grow a very large size crystal that has been done, but it's still not into large scale manufacturing.
Yeah. So the 100 microns that we're getting right now, this is without like any trick, for example, no special catalyst, no extraordinary flow rate of any kind. It's a normal copper substrate, standard growth, diluted methane, and we get the 100 microns. So in terms of using the data mining approach to enhance our synthesis, this is definitely our goal, but we haven't reached this point yet. We are working on a study. One student in the lab is working on the study to do exactly that. But to do that, we decided that first we wanted to have a design of experiments approach and not just use the crowdsourced or like all of the recipes we have. Basically design an experiment specifically to put it into the Gr-ResQ platform and then start using those experiments as the only data, because we needed a high level of control. This is something we're working on. We have like maybe 100 experiments or 120 experiments by now. The 120 experiments include repeats, so the independent parameters are maybe 30, like the independent recipes are maybe 30. Some of them are on the database already, some of them will be added, but we haven't really had a chance to start using these to explore new recipes.
What about the best graphene domains using trial and errors then?
It is, I'm guessing it's the same. I answered this already. The standard 100 micron domain size on regular copper catalyst. Okay. It seems that we're almost done here. I don't see new questions on the tools. But definitely your feedback and these questions that you're asking, like the features, right? So things like detecting the stacking based on Raman, doing specific consideration of the orientation of the grain of the catalyst and how it affects the Raman signal, and taking care of small features and small noise and so on. These are all things we're interested in. It helps us when users go and say this is in their wish list, this is a feature they would like to add. It helps us with prioritization, because there are so many things that can be done with each one of these tools. So add these to the wish list, and based on that we'll proceed. Yeah, so thank you all for attending. Mitisha, did you want to add anything?
Yeah, I just wanted to show that you can add your questions here. There's a wish list option over here and reviews option.
Can you zoom in a little bit, Mitisha? Yeah. This is the questions tab and the wish list.
Yeah.
Okay.
So this is on the main tool page. So you can just add your comments, etc. over here.
All right. Well, thank you. Thanks everybody for coming. And like we said, we hope you'll use these tools and use it to look for recipes, query recipes, contribute recipes. And as Sam said, we're also interested in your feedback and comments and ideas for how to make this more usable. Yeah, I think that's it. Thank you for coming and thanks for joining.